Hi, here we are again in doing this assignment 5 where we have to get the effects of ideal filter, and the overall assignment aim is to use Scilab to apply an ideal bandpass filter on a wave file recorded in assignment 2. So let's just listen to the previous wave file.
My name is Chu Hong Yi.
Alright, so all the tasks are, the first one is to use FFT to obtain frequency domain signal of the wave file recorded in A1. And second, we have to apply an ideal bandpass filter to remove all the frequency outside the usable voice frequency. In this case, a square wave as an ideal bandpass filter where it ranges between 300 Hz to 3000 Hz is used. And then after applying the filter, there is a reverse transform of the filter signal, and then we have to perform visual and auditory inspection on it. And then here we are doing all this screening. So we can see that the first line of the code reads the wave file from the directory, and then the second, it is followed by the calculating the total amount of seconds in the wave file, and the end is to determine the size of the and the number of samples from the fs from the y, and then the Fourier transform is applied through here, FFTY, and this F is to determine the range of the graph to be plotted in this in the Scilab. Then here is to determine the size of the n as well. So after that, there is a filter. We have to construct a filter on ourselves. We are advised not to use the built-in filter. And this line where we assign a variable of BPF equals to the arrays of 1 until the end of the size of the Fourier transform. And then for the range between 300 and 3000 Hz, we assign the value into 1. Okay, it is to determine the square wave where it is then multiplied into the Fourier transform, and here is it. So we take another variable of ppy, and then we multiply the filter into the Fourier transform, and then it is then have to carry out an inverse Fourier transform, and this variable of ibpy is set, and these codes are to function as the plot of the graphs for all the wave. So the first one is to determine the original wave file, and then the second one is to get the frequency domain of the first wave file. This will plot the filter wave, the wave of the filter, and then this is after the signal is multiplied with the filter, and then this one is the time domain of the filtered signal. So here we are. Let's take a look of the wave files. Yes, this is the original wave file, and then this is the frequency domain of the wave file. You can see that, and this is the filter from 300 to 3000, where it is a square wave as a bandpass filter. So this and this is multiplied and produce this wave file. We can see that it only ranges from 300 to 3000 kilohertz, 3 kilohertz. And then there's an inverse Fourier transform is done, and then it's back to time domain where all these are back again, come back to again. Let's hear the voice from this file.
My name is Chu Hong Yi.
Alright, what are the difference of these files as compared to the original one is that we can see that it's very obvious that the amplitude has changed from this 0.5 into 0.2. It's slightly smaller, yes. And the second one is that it can be seen that all these noise, not just noise, is the voice ranges outside this 300, between 300 to 3000 Hertz are eliminated when it was multiplied with 0. And we can see that actually these are smaller in after getting filtered, this part and this part. yeah, so actually there will be the ringing effect where we can hear it in our audio file, but it's not very obvious that you can listen to it. And yeah, that's all for this video, and thank you for watching.